Good morning, everyone. So welcome to my YouTube channel, Maths. So hope you are all good and you are doing well in your life. Okay. So today we are going to see second lecture on functions of bounded variation. Okay. So if you have not subscribed my YouTube channel, subscribe it for such type of interesting lectures. Okay. So let's start today's session now. So okay. In last class we defined what is functions of bounded variation. Okay. Okay. If F closed interval a, b to R, a and b are finite numbers, real numbers, b a function of bounded variation. Okay. Then we write, then we denote BFA, then we denote the total variation. Then we denote the total variation of F by BFAB. Okay. Sometimes we write VF in place of BFAB. Okay. We write BV functions of bounded variation function. BV means bounded variation. Okay. AB means what? Collection of all the F. AB to R is a function. Okay. And F is of bounded variation. Okay. So we are collecting all the functions of bounded variation on closed interval AB. Okay. And letting it BBAB. Okay. So next theorem is next result is very important. Let F AB to R be a monotone function. Okay. Then F is of bounded variation. And VF is nothing but FB minus FP. Okay. Let's see its proof. So F AB to R is a monotone function. Monotone function means either it is monotonically increasing or decreasing. Monotone function means it has two sense. Either it is monotonically increasing or decreasing. Okay. So we will prove first for monotonically increasing, then we will prove for monotonically decreasing. Okay. So assume that F is monotonically increasing. Monotonically increasing. Okay. For any partition P is equal to of AB. We have, okay, what we have? We have f x I minus f x I minus 1. Because function is monotonically increasing. So when function is monotonically increasing, fx minus fxi minus fxi minus 1 is a positive non-negative quantity. Okay. So this will be f. So this will be fxi minus xi minus 1 for I goes to 1, 2, 3 up to n. Okay. Reason is that since f is monotonically increasing. Okay. So what is we have? If it is monotonically increasing, fxi will be greater than equal to fxi minus 1. Okay. This implies fxi minus fxi minus 1 is greater than equal to 0. Once you have a non-negative quantity, then absolute value do not affect it. It will remain as it is. So this is equal to this. Okay. So that is why this is happening. So fxi is equal to fxi minus 1. Okay. Okay. Now what is this summation? What is SP? SP is equal to summation I goes to 1 to n fxi minus fxi minus 1. What is this? Tell me. Because if this is a from this, what we have? We can simply write it. This implies SP is equal to summation I goes to 1 to, and this is fxi minus fxi minus 1. Okay. Okay. So what is this? fxn minus fxn minus 1. Okay. This is, sorry, fxn fx1 minus fx0, okay, plus fx2 minus fx1, okay, plus fx3 minus fx2, okay. fxn minus 1, fxn minus 2, fxn minus 1, okay. Okay, so this is cancel out, okay, this is cancel out, okay. So this is cancel out by this, and this will be cancelled out by somewhere here, okay. What we got actually? So what we got? This is equal to, this is remaining fx naught and this is fxn. But as xn naught, xn is b, x naught is a, it means f. Okay, for any partition, okay, p, okay, of ab. Okay, so what does it mean? It means supremum p taking from row ab, sp is nothing but fb minus k. That is, and this is a real number. This is a real number. So it means supremum exists. It means this implies supremum p sp exists in R. Okay. So this implies f is function of bounded variation. Okay. F is function of bounded variation. Okay. Now what is total variation? VF is now, VF is nothing. What is supremum? This is supremum. P belongs to row A, B, okay, SP. But SP is nothing but FB minus FB. So this is fixed. So supremum will be this, because this is a fixed quantity. You take any partition. So what is this? So this is FB minus FB. So, okay. So we prove this, okay. Okay. So now, okay, because FB is greater than FA, because function is monotonically increasing. I can write like that. If I can put the mode, it will not affect anything. Putting the mode, it will not affect anything. So, because in theorems, it is given. Okay. Now, we have proved this theorem for monotonically increasing function. Okay. Now, we will prove it for monotonically decreasing. Now, assume that that F is monotonically, okay, decreasing. If F is monotonically decreasing, then C is equal to minus F is monotonically increasing. In this case, so following the same proof for following the same proof as above, we get what is SP for G. What is SP for G? That is because this is monotonic limit GB minus GA. I am calculating SP for G. So what will be this? GB minus GA. Okay. So what is this? What is the value of this? Is F minus B. This is minus FA. Okay. So FA minus FB. Okay. So SP for G. Now, so SP for F. Observe that SP for F is equal to SP is G. Okay, same thing. You can, I am writing SP genes, I am taking SP or F. Here I am taking SP of G. So this is FA minus FB. Okay. For any partition P of AB. Okay. Now this implies supremum of P taken over all the partitions at SP is nothing but FA minus FB. That belongs to real number. It means supremum P belongs to row A, B, SP exists. Okay. In R. Okay. So this implies F is function of bounded variation. F is function of bounded variation. Okay. Okay. Then what is the total variation? What is the total variation here? BF is equal to supremum P that is SP, but SP is nothing but that is FK minus FV, that is BF means FP minus FV. Okay. So I can take minus common. FB minus FP. Okay. So okay. Same thing I can write like that. FA FB minus FA. Okay. Because F is monotonically decreasing. F is monotonically decreasing means FA. Okay. So when it will come out of the modulus, minus sign will be there. So minus, if you're taking minus FB minus FA, so it will be minus FB plus FA. That is FA minus FB. Okay. So finally, what we prove? Therefore, every monotone function f from closed interval AB to R is a function of bounded variation and Vf is nothing but FB minus FA. So obviously, as F is monotonically decreasing, FB minus FA is positive, non-negative, so BF will be FB minus FA. If F is monotonically decreasing, then FB minus, after exiting from absolute value, it will be minus FB minus FA. That is FA minus FB. Okay. So this is done. Now corollary we have. So I am asking this question. Okay. I am asking this question. Is F x is equal to f to the power n functions bounded variation function on AB, where A and B belongs to real number. Okay. And A is less than B. It is easy to solution. Fx is equal to f to the power n. N is fixed. n belongs to n and n is 6. N is 6. Now you see that this is monotonically, f is monotonically increasing function. Okay. So here we are taking non-negative. Okay. 0, a is less than equal, a is greater than equal to 0. Okay. And less than b, strictly less than b. Okay. So I am writing this properly. So f(x) equal to x to the power n is monotonically increasing function. Okay. Okay. Monotonically increasing function on AB. Okay. Therefore, f is function of bounded variation bounded variation on AB. And what is the total variation? BF is equal to FB minus FA. That is B to the power n minus A to the power n. Okay. This is the answer. Example 2. Let fx is equal to c for all x belongs to AB. Okay. It means f is a constant function on AB. Okay. Then f is of bounded variation on f is function of bounded variation. How? Solution. We know that every constant function is monotonically increasing, decreasing both. Okay. Fx is equal to c. So this implies this is a constant function. Okay. Constant function. this implies f is monotonically increasing or decreasing both. So I am saying it monotonically increasing. It is monotonically, you can write monotonically decreasing as well. Of course. So this implies, so by theorem, f is function of bounded variation. Okay. So what is the total variation? What is the total variation of this? So BF is equal to FB minus FA. Monotonically increasing I am taking, so FB will be, so after taking from outside the absolute value, it will be FB minus FA. What is this? This is C, this is C. So total variation of a constant function is, every constant function is function of bounded variation and its total variation is 0. Now we are going to see some theorem, or you can say corollary. Corollary. Let A, B belongs to R and A is strictly less than B. Then F is constant on, then F, then a function F close interval AB to R is constant if and only if total variation of is 0. Okay. Proof. If f is a function from AB to R is constant, then total variation is 0. If total variation is 0, then function is constant. Okay. Okay. So how? First statement is trivial. F A AB to R is constant implies करता है BF is 0. This follows from example 2. This follows from example 2. Okay. Now conversely assume that BF is 0. Okay. So if BF is 0, it means supremum of SP over partition. It is finite. It means F is function of bounded variation. Okay. Okay. Now okay. Let x, okay, then consider first of all we know that FB minus FA is always less than BF, but that is 0 and this is non-negative. So this implies FB minus FA absolute value is 0. What does it mean? It means FB and FA, this is 0. It means FA is equal to FB. Okay. Now let x below x is such that I'm taking x. Now let x is in between. Then consider the partition P is equal to A. Okay. We have, okay. So what is this? Fx minus Fa plus Fb minus Fx. That is my Sp. But Sp is always less than Vf. Okay. Less than equal to Vf. But this is 0 and this is non-negative quantity. Okay. This implies, okay, this implies Fx minus Fa that is also less than Fx minus Fa plus Fb minus Fx. But that is also less than 0. So this implies Fx minus Fa is less than 0, less than equal to 0. So what does it mean? It means, okay, it means Fx minus Fa is 0. It means Fx minus Fa is 0. This implies Fx is equal to Fa for all x in this range. But we already proved that Fb is equal to Fa. So finally, let's say equation number 2 and let's say that Fa is equal to Fb, equation number 1. Okay. So from 1 and 2, from 1 and 2, we have Fx is equal to Fa for all x belongs to closed interval AB. Okay. Let's say C is equal to Fa. Then Fx is equal to FC for all X belongs to AB. This implies F is constant on closed interval AB. Okay. So today's lecture up to this. So what we learned in this lecture, we have seen that monotone functions are functions of bounded variation. Okay. By that fact, we proved that fx equal to x to the power n are functions of bounded variation on non-negative intervals. We also proved that constant function is also bounded variation function. Its total variation is 0. And if a function has a total variation 0, it means it is function of bounded variation. And it has a total variation 0, then it is functions of bounded variation. Oh, sorry, constant function. Okay. So today's lecture up to this. If you have any problem or issue related to this lecture, you can comment me on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Okay. So thank you very much for today's lecture. Thank you very much. We will see you in next lecture. Thank you very much.